recording. All right, thank you. Let's just remember this definition first. So we're talking about the representation. I'm going to use different letters for this. It's a representation of a group. And since it's a representation, it's a matrix, and that matrix acts on some kind of a vector space. This is actually usually these column vectors, since we are talking about matrices, but sometimes we may want to think about some abstract vector spaces. So as a result, we are going to get used to this kind of a language, right? So I may actually have representations of a group, not as matrices, but operators on acting on wave functions, for example. There are these kind of things are also possible. But in any case, this kind of a matrix representation language is actually appropriate for all of them for some reason. Okay, so V is the full vector space. And then we talk about some subspaces of V. We say that W is invariant if somehow if these representation matrices applied on vectors in that subspace always gives you the vectors in the same subspace, then we say that this is an invariant subspace. So I'm going to give you some examples for that, which essentially means that I don't know if you can see this part. It means that this A actually somehow is actually acting like a representation on that subspace too. So as a result, you can actually think of a smaller representation, but this time it's a representation on the subspace, okay? You can think of it like this. So there are these always the trivial subspaces. So these are the trivial subspaces. One of them is the null space. So it's the null space. And I'm going to call this as the full space. These are always invariant. These are invariant too. Invariant. And we are going to actually ask the question whether there can be some non-trivial, right? Non-trivial subspaces. So let me also say it like this. A is, we say, reducible if it has a non-trivial invariant subspace. It has an invariant subspace other than these two. So let me go back to...
Is this statement correct?
Which one?
Because the last one, because it implies that it must have a non-trivial invariant subspace, yes, but also it may include trivial subspaces too.
What do you mean?
I mean,
what this means is that it has an invariant subspace which is
that's correct,
other than these two.
This is not preventing to have a non-trivial subspace. This statement does not prevent that.
Does not prevent, yes.
So is it correct?
It is correct. So that's the definition. So we call the representation reducible if it has a non-trivial invariant subspace. So we say, let's also write it down like that. So it is irreducible if, let me say it like this, if no invariant subspace, invariant subspace other than the trivial ones. Okay, other than 0 and V, okay? So 0 and V, these are invariant no matter what the representation is, no matter what the group is, because these are trivial. Does the representation have an invariant subspace other than these? If it does, then we call the representation reducible, otherwise irreducible. Okay? let's talk about this representation that we have mentioned before. So I'm going to go there. So this is the representation. I think I'm going to hide the chat screen. In any case, I don't know if you can see the chat screen. So we have talked about this thing before. So that's a particular representation of the group S3, which is the symmetric group
Hocam, can I ask
permutations of
something?
3 objects. Excuse me?
Can I ask something?
Yeah.
From previous page.
From previous page, right? Yeah.
Yes. I didn't understand the last statement. It says A is irreducible if
There's no invariant subspace other than the trivial ones.
no. Oh, okay. Great, thank you.
I mean, forget about the trivial ones, right? I mean, let's just define the trivial subspaces as not, all right, they are actually invariant, but let's say that when we are talking about an invariant subspace, we just forget about the trivial ones, right? Because these are trivial ones. We call the representation reducible if it has an invariant subspace, okay? And it is irreducible otherwise. All right, let me give the example, all right? So that's going to be obvious. So basically reducible ones are the representations which I can express in terms of smaller representations. So I'm going to actually show that I can do this as a direct sum thing actually. So if it is reducible, then I can write it in terms of smaller representations. If it is irreducible, then I cannot. And in a way, these are the ones that are the building blocks of bigger representations. But at this point, there's no point in explaining this. So let's just go to this representation, right? This is the representation of the symmetric group. It's the permutations of 3 objects, right? And I have said this, so I can, well, we have the basic 3 by 3 representation of these permutations as permutation matrices, because these permutation matrices basically function as permutations of the standard basis vectors, okay? If you remember. So that's a nice representation. So let's say it like this. So first of all, we know that, for example, a vector of that kind is invariant under all, let me call this as, I'm going to use this language, right? I don't know, it's kind of awkward, but in any case. So if I have a vector where all 3 components are equal to each other, right? In that case, any permutation, that means just apply any permutation to these 3 labels, and I'm going to get the same vector. Okay? So as a result, if you think about these as vectors that are in a subspace, so let's call it like this. So I'm going to call this as W is defined as, let's say, vectors parallel to 1, 1, 1, right? So these are basically the vectors of that form. So A, where A is a complex number. I can also define it like this, right? W is a 1-dimensional subspace. Obviously. It also contains the 0 vector, obviously. So in any case, this is a particular subspace and it is invariant. W is an invariant subspace, subspace of the representation P. Okay. So P is a representation. P is this particular representation. P is this representation, basically. This set of 6 matrices, you can think of it as the representation. And under this representation, this tree, there are some subspaces in this 3-dimensional space which are invariant. So especially there is this 1-dimensional subspace. And so therefore, this implies that P is reducible. Okay. Some microphone is open, I believe. Okay. So therefore, it is reducible. All right, so we are going to see how we will reduce it. But you can think of it like this. Just note, remember the trivial representation that we have talked about before. It's a representation by one by one matrices. But basically, P behaves like a trivial representation on this subspace, because when it's acting on every vector in that subspace, it doesn't change it. It just multiplies it with one. Sorry about this. I'm sorry about that. Sorry. This is PG applied on this AAA gives you AAA, right? Which means PG applied on that vector gives me the same vector, right? In any case, yeah, just forget about the note in here. Okay. I don't know if you have any questions with this. There's another one in here, that vector space that we call as W-perp. This is called the orthogonal complement. Complement of W. I mean, this is the mathematical terminology. Let me actually express it like this. So this is basically the set of the vector, well, let's say the set of all vectors which are orthogonal to. Orthogonal means perpendicular, right? To every vector in W, right? Think of it like this. So we have some kind of a subspace in here. Let's say, all right, this is a one-dimensional subspace in here. Let me show it like that. So it is passing from 0 as well. So that's the 0 vector, whatever. So we define the W-perp. So let me use a different color for that purpose. W-perp as the subspace formed by all of these vectors, which are perpendicular to all vectors in W. So this subspace is basically is something like that. So you just think about every vector which is perpendicular to every vector of W, and all of such vectors form some kind of a subspace. So that's called the orthogonal complement, and whatever. So therefore, it has the property that it's defined like this. Okay. In any case, this is some kind of a Hilbert space terminology that the mathematicians use a lot, but I think that's something that I can use in here too. I can also describe this in the set constructor terminology. It's basically a vector where the sum of the components is always equal to 0. Right? Where, let me say, such that A1 plus A2 plus A3 is equal to 0. Okay. You can also think of this subspace like that. It's the orthogonal complement, but I can also describe it as basically any vector. Let's say it like this. I don't know. Let's say this is 2, 3, minus 5, for example. This is the set of vectors where the sum of the components is equal to 0. So under permutations of these labels, you can easily see that this property is going to be the same. So this is an element of W-perp. So just think about, for example, P1 to applied on V. So that's going to be the vector in here. So it's a different vector. It is 3, 2, minus 5. So that's also in W-perp. And I don't know, let's say 2, 3, or 1, 3, 2, for example, V, where the first entry goes into the third one, third entry goes into the second. Yeah, this one is in here, in W-perp, and etc. So therefore, W-perp is also invariant, is also an invariant subspace.
Hisham, can I ask something here?
Yeah.
Why do the components of V have to add up to 0? Or, I mean, any vector in W-perp?
It's the orthogonal complement of W. W is this vector. All the vectors spanned by this one.
Yeah, I'm asking what when you define W perp, why do the components have to add up to 0?
Because it's the, I mean, think of it like this. If V is this, A1, A2, A3, so W is this vector. It doesn't matter. All the other vectors are parallel to this. So it's the dot product in here is basically given by the sum of the components.
Oh, okay, okay. And they're perpendicular.
Yeah, this is the perpendicularity condition.
Okay, thank you.
So that's why we have this. But I mean, it doesn't matter. So you can also think of it like this, right? Just start with this definition. And you can see that after any permutation of these numbers, if they initially add up to 0, they also add up to 0 after that, right? Because permutation basically changes the places of these numbers. Okay, so it's clear that this is actually a subspace. And so therefore, this thing is an invariant subspace. Whether this is orthogonal to the other one is irrelevant, actually. Irrelevant at this point. Okay. Right, let me also show it like that, right? This is like somewhat like a three-dimensional picture. Right, this is an example. I think this is a nice example in here for these permutation matrices. I mean, there are these examples of these invariant subspaces. In any case, what does this have anything to do with the reducibility and things like that? Let's go back to the definition in here. So I'm going to start with this. So suppose that W is an invariant subspace. It is a non-trivial one, all right? So let me add it in here, right? So that's the new topic. So if W is an, let's say, is a D-dimensional invariant subspace for the representation A, all right? So the full space is, so let's say V is the full space. I'm just going to say that this is n-dimensional. Okay. So let's say that therefore D is a number between 0 and let's say that this is D is between 0 and n. It's not equal to any of them. So that means that's the same thing as saying that the W is non-trivial. Trivial, all right? So the trivial subspace, the null space has 0 dimensions. There's only one such subspace. And the full space has n dimensions. So any non-trivial invariant subspace has a dimension between these two extremes. Okay, what we do is this. I know that A is a representation. It's a matrix. I mean, it's a set of matrices. But these set of matrices correspond to transformations for a particular basis, which is chosen randomly. But now, since we have some kind of a subspace in here, then I can choose a new basis such that the, I don't know, where the first, let's say, D vector span this. So as a result, that's what I'm going to do. So this is the procedure. Choose a new basis for V. Let me write it down like that. V1, V2, dot, 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 Vn, such that, so the first thing is, let's say the first D vectors span W. VD. I think I explained this in the wrongest possible way. Is a basis for W. Okay. I think I need to say this. So since I have this subspace W in here, I just choose a basis for that subspace. All right. So let V1 to Vd be such a basis. And then I find, once I constructed this basis, then I find new vectors, Vd plus 1 to Vn, such that this set plus this set is a basis for the full space, all right? Probably I should say this. Okay, is a basis for V. In any case, what I'm going to say is that if I express the representation matrices with this basis, then the matrices become simpler. So that's what I need to actually explain. So note, right, T of G, V1, sorry, what is T of G? I'm sorry about this. There is no T of G, A of G. So G is a group element, whatever it is. A of G is the representation matrix. I know that when A of G is applied on V1, I'm going to get some set of matrices in here. I don't know, let's call it like C1, V1, plus C2, V2, and so on. But it's just going to be a linear combination of these first D elements. Okay. So I'm just going to repeat the same argument again. So FG VD, for example, because of the invariance property in here. So let me call this as C1 prime V1 plus C2 prime V2 plus CD prime times VD, right? So because of the fact that the W is invariant subspace and this V1 to VD are just is just a basis for that W, we get this property. But for vectors for VD plus 1, so I'm going to get something else in here. So that's going to be V1 dot 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 dot, and so CD double prime VD, but I'm going to continue for these ones. So CD plus 1 double prime VD plus 1, and so on. All right, so I'm just going to continue with the same kind of a thing, right? But let me just cut the story short, right? So there are going to be many terms in here. Okay, so this is the essential idea in here. So as a result, if I do express this linear transformations in this basis, which essentially means a similarity transformation, so that means that there is a similarity transform so let me say it like this. Each A of G would be expressed as, like, let's say B of G, which is S inverse A of G S, where this B of G is basically A of G, but expressed in this basis, all right? So if I then write this thing down, write these matrices, just keep in mind that V1 is the first standard basis vector for B of G. So in any case, let me just say it like this. B of G then has a matrix expression like that. So in the first column, I'm going to have these first D coefficients and zeros for the rest. Okay, so what I would like to do is, what I do in constructing these matrices is basically write down these coefficients in a column. And when I write them down, so I'm going to have zeros at some point, after some point, right? Let me just do it like this. So as a result, the first D columns of that B of G matrix would be something like this. Okay. And the other ones, these are a little bit more complicated, right? So these actually span all the columns, all the rows, sorry about that. In any case, I'm not just going to write these things down, but you should actually get the essential idea in here. So if I express this representation in a basis where the first D vector span this invariant subspace, in that case, the new representation would basically look like this. So the first D columns and D rows is going to have some kind of non-zero entries in here. So that's going to be a block in here. There's going to be some block in here too. So all of these X's represent some non-zero blocks. And there's some kind of a block in here, but we will have zero entries in this subblock. Okay. Right, this is actually a very complicated way of writing this thing down, but I'm just going to simplify it. So there's a block in here, which is essentially a square matrix with size D. There is a block in here, which is also a square. There's also another block in here, which is rectangular. This block is 0, right? Let me then write this thing down. So the best thing that I can do in here is to do this draw these pictures basically, okay? So we have some kind of an n by n submatrix in here. There's an n minus, sorry about that. This is d by d. Sorry, this is a d by d square matrix. This is an n minus d by n minus d square matrix. And this is d by n minus d rectangular matrix. And this part is n minus d by d zero matrix. So that's a zero matrix. Okay. So in any case, basically this tells you that in a, if I have some kind of an invariant subspace, then I can find a suitable similarity transformation which makes some subblock of these matrices to be equal to 0. Okay? And as a result, this is basically what I'm going to do. So this is a similarity transformation from A to B. So that's a similarity transform. B of G. And B of G has these blocks in here. So I'm just going to use this notation in here. I think, yeah, sorry about that. So I'm going to use this notation. So I'm going to use, let's say I'm going to give a name to this. So I'm going to call this as like f of G. This is, I don't know, h of G. This is L of G, for example. I'm going to use a big 0 in here, right? So that big 0 represents a 0 matrix, essentially, right? Sorry about this, because I cannot use a better notation than this. So how do you represent a 0 matrix? I mean, this is basically some kind of a rectangular matrix with sizes like that. So we just call this as a 0 matrix. It's a matrix where all entries are equal to 0. It is rectangular. The dimensions do not need to be the same. In any case, when I write down this kind of a block notation, all of the diagonal blocks are always square, right? So therefore, this is d by d, and this is n minus d by n minus d. This is in general rectangular, but sometimes accidentally it can also be square as well. Okay. So let's say it like this.
Hocam,
yeah.
If you are not comfortable with the notation, maybe you can express its size like 0 n minus d cross d.
Yeah, this one, but yeah, sometimes I don't want to do that too. So let me also write down this notation too. So this is 0 n minus d cross d. So it's a 0 matrix of that size, yes. So that's something that I need to do, but sometimes this is, I mean, writing too many things is actually takes too much time. And so as a result, for economy, I usually do these kind of shorthands. And sometimes I don't even write this thing down because There are so many zeros there that I cannot write them down. So as a result, I don't write anything. Okay, so where f of g and L of g are square matrices. And h of g is rectangular. In general. Okay. So why do we do this? Because it simplifies the matrix expressions. Okay, so that's the important point. And that's why we are interested in, because we will have some kind of representations, given representations. We would like to express these given representations in terms of smaller ones. And that's the way to do it. All right, so as a result, the existence of the invariant subspaces somehow is a nice property. In that case, this would imply that I can make these matrices simpler. Okay, so basically we are going to do this in general. So this is something that I'm not going to use in here, but you can show this. Right? Show that f of g and these diagonal blocks are representations of the group. They are representations of the same group, obviously. So we're talking about the same group all the time, every time. So if a big representation is reducible, by this method you can find smaller representations. Basically, the diagonal blocks would be smaller representations. This h of g is not a representation because it just satisfies some strange property that I don't want to mention here. It's not necessary to mention about this. Okay, I don't know if you have any questions or not.
This looks a very nice way of partitioning the representation, but is it possible all the time to find such bases? Because it could be cumbersome to solve all of those questions to find coefficients or suitable bases. Is it possible all the time?
To do it practically, you mean?
Yeah, practically. Theoretically,
yeah,
that's okay.
We are going to have some other procedures for finding the appropriate bases.
I see.
Problem with this. So this is basically whether I can reduce the. All right, this is just some mathematical basis. So we are going to later see a little bit more advanced, much quicker ways of actually identifying these subspaces and then finding bases and things like that. Okay, it's not a big problem. All right, so we are just thinking about this. So in any case, this is good, but it's not good enough. So the question is, can I also make this off diagonal block 0 as well? Okay, in that case, it appears that sometimes yes, sometimes no. All right, so in that case, we have another definition. Okay, so let me say it like this. I'm sorry about this because most textbooks, most physics textbooks doesn't mention about this. So we say that the representation A is called decomposable if first it has it's not the first of all, right? It has invariant subspaces in, sorry about this, let me write this clearly. So invariant subspaces W and W prime such that, first of all, these two subspaces basically are different from each other. They don't intersect except at 0 vector. So their intersection is the null space. And the second thing is that their sum is basically the full space. this is actually some kind of a decomposition of the vector space into these two subspaces. So I think, I don't know the correct English term for these, but I remember that, for example, a plane and a line that doesn't lie inside that plane is called an ayrık, for example. This is actually called ayrık in Turkish, but I don't know the correct term here. So this is basically such an example. So it's there's a two-dimensional subspace in here and a one-dimensional subspace. They don't have any, they actually intersect because all of the subspaces somehow should contain the zero vector. They intersect, but their intersection is only zero. Moreover, I can express every vector in the full space as a sum of vectors in that these two subspaces. So let me kind of show it like this, right? So let's say it like this. This is just another comment in here. So every vector in V can be expressed as a sum of vectors in these subspaces in a unique way. And that's essentially what it means. So if I have some kind of a vector in the full space, in that case, I can find vectors W in W and W prime in W prime, such that, right, V is equal to W plus W prime. I don't know why I'm explaining this, but in any case, what's the usefulness of this? So let me actually use this kind of a thing in here. So let's say it like this. Find a basis V1 to Vd for W, and then find a basis for the other subspace. And let me call the vectors in that case Vd plus 1 to Vn for W prime. So in that case, their sum is, if I just concatenate that list, so that's a basis for the full space, is a basis for V. In that case, I can make this similarity transformation where A of G is similarity transformed into similarity transform into another representation where, well, basically the first column of the block, basically the representation matrix is acting on the vectors in the subspace W. So I have some kind of an, I think I call this as f of G in here. And then I have the representation which is restricted on the W subspace. So I have the representation LG in here. And I have 0 blocks in here and 0 blocks in here. Okay. And I'm not, apart from that, I'm not going to explain how it happens. But basically, a representation is, if it is decomposable, in that case, we don't need just a single invariant subspace, but we have 2 invariant subspaces. In that case, by a suitable choice of the basis, I can bring the matrix, the representation matrices into this block diagonal form. So that's called the block diagonal. Okay, so think of it like this. So, right, A is reducible means that's the same thing as saying that A can be, there is a similarity transform such that A can be brought into this form where we have matrices in here and 0 matrix in here. A is decomposable means That's the same thing as meaning that I can do this where I can bring the whole representation matrices into the block diagonal form, right? So if it is reducible, if it is in this upper triangular form, if it can be made into this upper triangular form, it is decomposable if it can be made into a block diagonal form. Okay, there's a subtle difference between these two. Fortunately, there's no difference between these two concepts if the group is finite. Okay, so let me actually show it like this. I'm just going to write it down like that, right? If G is a finite group, this is critical. In all of our examples, we are going to do the discussion on a finite group. So whenever we meet an infinite group, we will just get scared and we don't do anything, right? But let me add a small note in here, or a compact Lie group. I'm going to explain what that means. So Lie group is basically a continuous group, but it has to be compact, right? A representation is reducible if and only if it is decomposable. So the reducibility and the decomposability are the same. So if you can transform a matrix into that form, that essentially means that you can also transform it to this form, right? So as a result, we won't make a distinction between these two. And that's the nice thing about the representation theory of finite groups, because the reducibility criterion is a little bit simpler than the decomposability criterion. And so therefore, we will be talking about the reducibility and irreducibility, all right? So that's the nice thing, right? Let me just say it like this. Let me call this as the theorem 2. So that's, let me write it down like that. So that's the theorem 2. I'm going to show it by showing this other thing in here. And this is the one that I'm going to provide the technical details for. So if G is a finite group, right, or a compact Lie group, the same argument. Then every representation is equivalent to a unitary representation. Okay, so by this, we enter into the wonderful world of unitary representations. So in any case, I can basically do a similarity transformation and convert every representation to a unitary representation. And in applications, we are going to see the reason for that. But let me say it like this. First, in quantum mechanics, every representation of, especially for finite groups, finite symmetric groups, every representation will already be a unitary representation, because we are going to start with unitary representations in any case, okay? Because somehow in quantum mechanics, there is this kind of a thing. So a symmetric transformation always corresponds to a unitary operator acting on the wave function, right? That's the first thing. So I'm going to also talk about this. For classical vibrational problems, sometimes it might appear that a given representation may not be unitary, but by a suitable choice of the coordinates and things like that, we can always make them as unitary. And you can think of it as part of this theorem too. In any case, what I'm going to do is, first I'm going to show the theorem 1. And after that, showing the theorem 2 is very easy, actually. It's a very simple thing. So as a result, that's what I'm going to do in the next hour. Okay. So again, let me repeat, this is the technical part. So once I prove this theorem, we are not going to do anything with it anymore, except that we are going to use the result that, for example, we are going to choose every irreducible representation as a unitary representation, for example. I don't know, because this is a little bit more convenient. For this one too, all right? Once we prove this, we are not going to revisit these kind of things again. So as a result, this part is somehow things that perhaps you can forget later on, okay? But I mean, there are some techniques that we are going to use in here that we are going to repeat later on, proof techniques. And so this part is a little bit important, okay? In any case, let me come back to this. I think the essential idea is somewhat in here. So this representation, this particular representation, this is actually a unitary representation. Actually an orthogonal representation where every matrix is an orthogonal matrix, right? And the nice thing in here is that if you find an invariant subspace about the unitary representation, basically, if you find an invariant subspace, the corresponding orthogonal complement appears to be also invariant, right? That's something that's quite easy to show, and that's basically what how I am going to actually prove the theorem too, right? So in any case, so that part would be very simple. So let me go to that part again. So that's the last point that I'm left, all right? So let me add this to, yeah, I'm going to bookmark this. So we will continue with this. As a result, let's give a break in here. So let's meet at 11:40. Let me stop the recording. And if you have any questions, I'll take the questions.